Hi, hello, this is Gary, teaching 10th Mathematics, the chapter Real Numbers. Introduction of the concepts of the chapter. Hello dear students, here is the first chapter of our 10th class textbook. You see, look at this diagram. What can you see in this diagram? Yes, it is a bunch of roses. Now, how many roses are there? You count. Yes. If I ask you to count, you may start from 1. You may say 1, 2, 3, 4, 5, 6, 7, 8 and 9. Therefore, there are 9 roses in this bunch of flowers. Look at this diagram. These are our freedom fighters. If I ask you to count how many are there, then you may start counting like this: 1, 2, 3, 4, 5, 6 and 7. In this diagram we have 7 famous freedom fighters of India. If we look at this diagram, here are our Indian soldiers, and these soldiers are hoisting a flag and they are safeguarding our border. And if I ask you to count how many soldiers are there, then how do you count? Yes, you can start from 1. You may say 1, 2, 3, 4, 5, 6, 7, 8 and 9. You may say that there are 9 soldiers, and these 9 soldiers are safeguarding our territory with our national flag in their hands. Look at this diagram. This is the moment when our Indian cricket team won the World Cup. If I count how many Indian players are there in the team, then how can you count? You may start from 1. You may count like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. You may say that there are 15 members in our Indian cricket team who won the World Cup. You see, in all these cases, you started counting from 1 and you counted like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and so on. These numbers are used to count the objects. Therefore, these numbers are called counting numbers. Okay? You can use the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and so on. You can use these numbers to count the objects. Therefore, they are called counting numbers. And you see, if you look at the numbers may start from 1 in this case. You may start counting from 1, 2, 3, 4, 5, 6, 7, 8, 9 and later by getting a number 10 in which we have 1 and 0. In the next number 11 we have 2 1s, and in the next number 12 we have 1 and 2, like this. Therefore, we use the digits 1, 2, 3, 4, 5, 6, 7, 8, 9 and 0. These 10 are called digits, and these digits are useful to form numbers. Any number can be formed by these 10 digits only. Therefore, how many digits are there? We have 10 digits. And what are they? 1, 2, 3, 4, 5, 6, 7, 8, 9 and 0. These 10 are called digits, and we can form numbers by means of these digits. You see, for example, 1, 5, 10, 13, 28, 99, 123, 999, 1000 and so on. And all these numbers are formed by means of these 10 digits. Now, what are the different types of sets of numbers? You come across these sets of numbers in your previous classes. Yes, the first set of numbers is set of natural numbers. Natural numbers is denoted by the letter n, and these set of natural numbers may start from 1. 1, 2, 3, 4 and so on are called set of natural numbers. In this set of natural numbers, what is the least natural number? Good. 1 is the least natural number. And what is the highest natural number? Good, we cannot say. Therefore, the infinity is the highest or the maximum natural number. There is no highest natural number, but the least natural number is 1. Now, the difference between any two successive natural numbers is always 1. And again, if you add 1 to a preceding natural number, you will get the next natural number. For example, if you add 1 to 1, you will get 2. If you add 1 to 2, you will get 3. If you add 1 to 3, you will get 4. If you add 1 to 4, you will get 5. And so on, you can write all these natural numbers. Since n is the first letter in the word natural numbers, these natural numbers are denoted by the letter n. Next is whole numbers. Whole numbers may start from 0. 0, 1, 2, 3, 4 and so on is set of whole numbers. And this set of whole numbers is represented by the letter W. This set of whole numbers is nothing but the set of natural numbers plus 0. If you add 0 to set of natural numbers, you will get set of whole numbers. Therefore, you can write set of whole numbers as 0 and this is union. 0 union n means natural numbers union. Unions means you have to sum up. Natural numbers plus the number 0. You will get set of whole numbers. And the next is set of integers. Set of integers is represented by Z. You see, the set of natural numbers is represented by n and set of whole numbers is represented by W, as W is the first letter in whole numbers. But whereas in this case, integers are represented by Z but not by I. Why? Because these integers are also called as Euclids numbers in German. In German, you can call integers as Euclids numbers. You can represent the integers with Z, Euclids may start with Z, therefore these are represented by Z. These integers may start from minus infinity to minus 2, minus 1, 0, 1, 2 and so on. This is nothing but the negative numbers union whole numbers. If we add negative numbers to the set of whole numbers, you will get integers. And in other words, if we add negative numbers and 0 to set of natural numbers, again you will get integers. The next set of numbers is rational numbers. The rational numbers is represented by the letter Q but not with R. Q stands for quotient. You see, rational number is a number which is in the form of P by Q. Any number in the form of P by Q is called a rational number, but the condition is P and Q should be integers and Q should not be equal to 0. Rational numbers represented by the letter Q, and a number in the form of P by Q where P and Q are integers and Q not equal to 0 is called a rational number. A rational number is a number which is in the form of P by Q, a fraction form P by Q, numerator by denominator, where both numerator and denominator should be integers and Q should not be 0. The denominator should not be 0. Such type of numbers are called rational numbers, and these rational numbers are represented by the letter Q. Q stands for quotient. Every natural number is a rational number, every whole number is a rational number, every integer is a rational number. Therefore 0, 1, minus 3, 1 by 2, minus 4 by 5 and all these are rational numbers. If you come to decimal numbers, 0.125, this is the terminating decimal, a rational number. Every terminating decimal is a rational number. This is 0.333 and so on. It is non-terminating but recurring. 3 is repeating. Therefore, non-terminating and recurring decimals are also rational numbers. And this is 12.4 and 7 is recurring. Therefore, it is again a rational number. And square root of 4. Square root of 4 value is 2. Therefore, root 1, root 4, root 9, root 16, root 25 and all these are rational numbers. If it has perfect square root, then they are called rational numbers. Okay. Therefore, what is a rational number? A number which is in the form of p by q, where p and q are integers and q not equal to 0, that is denominator is not 0. Both numerator and denominator should be integers. Such type of numbers are called rational numbers. Please keep in mind, every natural number, every whole number and every integer is a rational number. You might have a doubt that if you look at 0, how 0 is a rational number? Because can you write 0 in the fraction form? You may have such doubt. Yes, 0 can be written in the fraction form. How? You can write 0 as 0 by 1, 0 by 2, 0 by 3. Therefore, it is in the form of p by q, where 0 numerator is a rational number and of course denominator is not 0. 0 by 1, 0 by 2, 0 by 3. Therefore, it is a rational number. 1 means 1 by 1. You can write 1 as 2 by 2. You can write 1 as 3 by 3. Again, it is in the p by q form. Therefore, it is a rational number. Minus 3 means minus 3 by 1. Minus 6 by 2. Like this you can write. Therefore, this is also a rational number. Okay, is your doubt clear? Good. Note, all terminating decimals and non-terminating recurring decimals are always rational numbers. You see, I told you already. 0.125, it is a terminating decimal. 0.333 and so on, it is non-terminating recurring decimal. And 12.4777, therefore it is 12.4 and 7 is recurring, therefore again it is non-terminating recurring decimal. All terminating decimals and all non-terminating recurring decimals are always rational numbers. And the other type is irrational numbers. As you know that the rational numbers are represented by q, now irrational numbers are represented by q dash, or they are also represented with s. An irrational number is a number which is not rational. Right, 1, 2, 3. An irrational number is a number which is not rational. Every non-rational number is called an irrational number. Here are the examples for irrational numbers. Root 2, root 3, 1 by root 2, root 2 plus root 3 minus root 5, and 3.125682726 and so on, and pi. All these are examples for irrational numbers. Root 2, if you find the square root of 2, you will get a non-terminating and non-recurring number. And root 3 is also non-terminating decimal. 1 by root 2, root 2 plus root 3, and root 3 minus root 5, 3.125682726 and so on. Here, if you look at this decimal number, this is non-terminating, it has no end, and at the same time, nothing is repeating. It is not a recurring number, and it is not a terminating decimal. This type of decimal numbers are called irrational numbers. And again, pi is also an irrational number. Generally, in the place of pi, you may write 22 by 7. As you wrote pi in the form of a fraction 22 by 7, why it is not a rational number and how can you say that it is an irrational number, you may ask. Here, even though you can write pi is equal to 22 by 7, it is not its exact value. Pi value is not exactly 22 by 7. It is nearly equal to 22 by 7. The value of the pi is very nearly equal to 22 by 7. Therefore, it is an irrational number. Here is the note. Non-terminating and non-recurring decimal numbers are called an irrational number. If you look at these different types of numbers, you may come across natural numbers, whole numbers, integers, rational numbers, and irrational numbers. But our chapter is real numbers. Now, what is a real number? So far, you know natural numbers. You come across whole numbers. You learn what are integers. And you understood what is a rational number. And you also learned that how a number is an irrational number. Now, what numbers are called real numbers? This is the name of the chapter actually. What are called real numbers? A real number is nothing but a union of rational and irrational numbers. If we join rational and irrational numbers together, then they are called real numbers. Means the union of rational numbers and irrational numbers together are called real numbers. Real number is nothing but the union of rational numbers and irrational numbers. Q union Q dash is set of real numbers, or Q union S is set of real numbers. S is used to represent irrational numbers. Q dash is also used to represent irrational numbers, whereas this Q is used to represent rational numbers. Therefore, the union of both rational and irrational numbers is called set of real numbers. If you observe this diagram, you can find here is the first circle. This is set of natural numbers. Natural numbers may start from 1, 2, 3 and so on. And this is set of whole numbers. The set of whole numbers may start from 0, 1, 2, 3 and so on. Therefore, every natural number is a whole number. The circle N is included or inside the circle W. Therefore, every natural number is a whole number. Now this is the set of integers. Set of integers may start from minus infinity and end with plus infinity. Therefore, every natural number is an integer and every whole number is an integer. And besides whole numbers, there are negative numbers also in integers. Therefore, both natural numbers and whole numbers are inside the set of integers. And this is the set of rational numbers, which are in the form of p by q and q not equal to 0, and both p and q are integers. This is set of rational numbers. Every natural number is also a rational number, every whole number is also a rational number, and every integer is also a rational number. You see, the circle N and the circle W and the circle Z are the parts of the total circle Q. Therefore, all these numbers are included in set of rational numbers. The different circle represent the set of irrational numbers. Therefore, the numbers which are not rational are called irrational numbers. These irrational numbers are represented by Q dash or S. Now, if you include the set of rational numbers and the set of irrational numbers together, if you sum up all these rational and irrational numbers, you will get set of real numbers. Now you see here it is the fundamental theorem of arithmetic. Let us see its statement. The fundamental theorem of arithmetic states that every composite number can be expressed as a product of prime factors in an unique way. I shall repeat, every composite number can be expressed as a product of prime factors in a unique way. Means in only one single way. Unique means in only one way. You may try to understand. First of all, what is a composite number? Composite numbers means a number which is having more than two factors is called composite number. A number with exactly two factors is called prime number, and a number which is having more than two factors is called composite number. Now every composite number can be expressed as product of prime factors in only one way. Now let us try to understand this statement with a given example. Now if you look at this example, 30, you can write 30 as 2 into 3 into 5. 2, 3, 6, 6, 5 is 30. You see, you can write 30 as the product of three prime numbers. 2 is a prime number, 3 is a prime number, and 5 is a prime number. You can write 30 in only in this way, and you cannot write 30 in any other way as the product of prime numbers only. Of course, you can write 30 as 6 into 5, but 6 is not a prime number. Therefore, you can write 30 as the product of prime numbers in only one way, and there is no other way. Similarly, look at 36. You can write 36 as 4 into 9. This 4 is 2 into 2, and this 9 is 3 into 3. 2 into 2 is 2 square, and 3 into 3 is 3 square. Therefore, you can write 36 as 2 square into 3 square. We can write 36 as the product of prime numbers in only one way. Similarly, 60. 60 is nothing but 4 times of 15. 4 is 2 square and 15 is 3 into 5. Therefore, 60 can be written as 2 square into 3 into 5. This is the only one way in which 60 can be written as the product of prime numbers. This is called fundamental theorem of arithmetic. Every composite number can be expressed as the product of prime factors in a unique way. Now go for another example, 420. This 420 you can write it as 2 into 210. Again you can split 210 as 2 into 55, and you can split this 55 as 5 into 11. Therefore, finally 420 is equal to 2 into 2 into 5 into 11. 2 into 2 is 2 square into 5 into 11. Therefore, 420 can be written as the product of prime factors as 2 square into 5 into 11. This is again an unique way. This is what is fundamental theorem of arithmetic. Note, writing any composite number in this form is called exponential form or prime factorization method. You see, you wrote 30 as 2 into 3 into 5, and you wrote 36 as 2 square into 3 square. You wrote 60 as 2 square into 3 into 5. We wrote 420 as 2 square into 5 into 11. All these numbers can be written as the product of prime numbers. This type of writing all these numbers is called exponential form, and the method is called prime factorization method. The next concept is HCF and LCM. HCF stands for highest common factor and LCM stands for least common multiple. You come across what is HCF and what is LCM in your previous classes. Now here is a question. Find HCF and LCM of the numbers 60 and 75 using prime factorization. I shall repeat. Find HCF and LCM of 60 and 75 using prime factorization. Here is the solution. First of all, write 60 as the product of prime factors. 60 is nothing but 2 into 30. Again 2 into 2 into 30 is 15. Again 15 is 3 into 5. Therefore, 60 is 2 square into 3 into 5. And the second number is 75. 75 can be written as 3 into 25. This 25 can be written as 5 into 5. Therefore, finally 75 is equal to 3 into 5 square. Now we wrote the factors of 60 as 2 square into 3 into 5, and we wrote the factors of 75 as 3 into 5 square. Now we have to find the HCF. HCF means it is the product of common factors with their respective least exponents. Here HCF is nothing but the product of common factors with their respective least exponents. We look at these two products. Here what are the common factors you pick up? Here the factor is 2, but there is no 2 in 75. Here is a factor 3 in 60. 3 is also a factor of 75. Therefore HCF is equal to 3 in 2. Here 5 is a factor of 60 and 5 square is a factor of 75. Therefore, which is common? 5 and 5 square, the common is 5. Otherwise, now out of these common factors, here the exponent is 1, here the exponent of 5 is 2. Therefore, what is the least exponent? 1. Therefore, you have to consider 5 only. HCF is 3 into 5. These are common factors in both 60 and 75. What is the product of 3 into 5? 3 into 5 is 15. Therefore, HCF of 60 and 75 is equal to 15. HCF is nothing but the product of common factors with their respective least exponents. Now let us find LCM. In finding LCM, we have to consider the product of different factors with their respective highest exponents. In the previous case, we took common factors and we took the least exponents. And in finding LCM, we have to take all different factors with their highest exponents. You see, here 2 is a factor, but here there is no 2. Even though there is no 2 in 75, you have to take this 2 square to find LCM. The highest power of 2 here is 2, and here the highest exponent of 2 is 0. Therefore, you have to consider 2 square. Here we have 3. Here also 3. Therefore, take 3. Here we have 5, but here 5 square. What is the highest power? 5 square. Therefore, take 5 square. And you find the product of all these. 2 square is 4, and this is 3. 5 square is 25. 4 into 3 into 25. 425 is 100 into 3 is 300. Therefore, the product of different factors with their respect to highest exponents is LCM, and the product of common factors with their respect to least exponents is HCF. Hello students, are you attentive? Okay. Here is the next concept. This is Euclids Division Lemma. Let us know the statement of this Euclids Division Lemma. The statement is, given positive integers a and b, then there exists a unique pair of integers q and r satisfying a is equal to bq plus r, where r is greater than or equal to 0 but less than b. This is the statement of Euclids Division Lemma. I shall repeat. Given positive integers a and b, then there exists a unique pair of integers q and r satisfying a is equal to bq plus r, where r is greater than or equal to 0 and but less than b. Now let us try to understand this division lemma with a simple example. For example, if we divide 7 with 2, then you can write 7 as 2 times of 3 plus 1, isn't it? You see, look at this. Look at this division. Here this is the division. If you divide 7 with 2, this 2 in 7 3 times. 3 2 6, and if you subtract 6 from 7, you will get 1. Now this is dividend. 7 is the dividend and 2 is the divisor, 3 is the quotient and 1 is the remainder. Good. Now you can write this. Now you can write this 7 as the product of 2 and 3 plus the remainder 1. This is division rule. Dividend is equal to divisor into quotient plus remainder. Therefore, you can write 7 as 2 into 3 plus 1. You see, if we divide 7 with 2, then 7 is equal to 2 times of 3 plus 1. The remainder should always be either 0 or less than the divisor. Here, if we divide this number with 2, the remainder should not be 2. It should be less than 2. Similarly, if we divide this number with 3, the remainder should be either 0, 1 or 2. Since we are dividing this 7 with 2, this 7 is equal to 2 times of 3 plus 1, and this 1 means remainder should be greater than or equal to 0 but less than the divisor 2. This is the Euclids division lemma. Now, here if you look at the statement, there are two integers a and b, where a is greater than b. Since a is greater than b, you can divide a with b. If you divide a with b, then there may be some quotient. Let us name the quotient as q. And there may be some remainder. Let us take the remainder as r. Now if you divide a with b, then b in a quotient times. And if you get the quotient, then you have to multiply these two. B into q is bq. And if you subtract bq from the dividend a, you will get r. So that you can write the a value as b into q plus remainder r. You see, a is equal to bq plus r. Here the remainder should be, here what is the remainder in this case? The remainder is r. Therefore the remainder should be greater than or equal to 0, but it should be less than b, less than the divisor. You compare this with this given example, so that you can understand very easily. You see, the statement is, given positive integers a and b, then there exists an unique pair of integers q and r satisfying that a is equal to bq plus r, where r is greater than or equal to 0 but less than b. How can you understand this? By taking 7 and 2. If you divide 7 with 2, this 2 in 7 3 times, 3 2 6 and the remainder is 1. Therefore you can write 7 as 2 times of 3 plus 1. You can write 7 as 2 times of 3 plus 1. Where the remainder 1 is greater than or equal to 0 but less than the divisor 2. Similarly, if you divide a with b, there are two integers a and b. If you divide a with b, then there is some coefficient q and the remainder is r. Therefore you can write this a by using division rule as a is equal to b into q plus r. If you go for any division, either the remainder is 0 or the remainder may be positive value and it should be less than this divisor. Therefore, r should be greater than or equal to 0 but less than b. This is Euclid's division lemma. Now, let us find the HCF of 50 and 70 using Euclid's division lemma. It is a very important model as far as the public exams are concerned. Look at the question again. Find the HCF of 50 and 70 using Euclid's division lemma. HCF is also called GCD. You may please keep in mind. HCF means highest common factor and GCD means greatest common divisor. Factor and divisor are both same. Highest common factor is HCF. GCD means greatest common divisor. Both are same. Find the HCF of 50 and 70 using Euclid's division lemma. Here is the solution. Now let us write the statement of the division lemma first of all. Given positive integers a and b, then there is an unique pair of integers q and r satisfying a is equal to bq plus r, where 0 is less than or equal to r is less than b. Now, using division rule, out of 50 and 70, we have given two numbers 50 and 70 now. Out of these numbers 50 and 70, the biggest number is 70. Now we have to divide this 70 with 50. Now this 50 in 70 one time. Therefore 70 is equal to 1 time of 50. What is 1 into 50 is 50. Now if you subtract 50 from 70, you will get 20. Therefore the remainder is 20. 70 can be written as 50 times of 1 plus 20. Here a is equal to 70, b is equal to 50 and q is equal to quotient is 1 and the remainder is 20. Here the remainder is not 0. We have to do this same division rule till you get the remainder 0. Now in the first case you took 70 and 50. And in the next case, we have to consider the divisor and the remainder in all the steps. Now you consider 50 and 20 now. Out of 50 and 20, 50 is greater than 20. Therefore, divide 50 with 20. Now you can write 50 as 2 times of 20. What is 2 times of 20? 40. And what is the remainder? 10. Therefore, 50 is equal to 20 into 2 plus 10. Here a is equal to 50, a is equal to 50 and b is equal to 20, q coefficient is 2 and the remainder is 10. Again the remainder is not 0. Since the remainder is not 0, again you have to go for the next step where you have to consider the b value and the remainder. You have to consider the divisor and the remainder. Divisor is 20 and the remainder is 10. Now consider 20 and 10. Now if you divide 20 with 10, you can write 20 is equal to 2 times of 10 plus 0. Here you get the remainder 0. Since the remainder is 0, in this case, what is the divisor? At the step of getting 0 in the remainder place, what is the divisor? Divisor is 10. Since the divisor is 10, the HCF of 50 and 70 is equal to 10. In this process, you have to find the HCF of two numbers using Euclid's division lemma. And we will learn some more questions from the exercises of the chapter Real Numbers in the next video. Thank you one and all.